Hello everyone, in today's video I would be giving a quick summary as to how to solve problems based on NTU method. Now the trick to identify whether a problem is based on the NTU method is that whenever you see the terms such as NTU or effectiveness in the question, we need to go about with this method. The method is pretty simple and it consists of 3 or 4 formulas which we'd be seeing right now. Referring the data book, these are the two formulas related to effectiveness based on the flow, whether if it's parallel flow or counter flow. I would be taking you through the formulas first and then we would be solving a problem related to it. So as we see for a parallel flow, the effectiveness is given by this equation. In order to put it in simple terms, I can write the effectiveness is equal to 1 minus e power negative n times 1 plus c over 1 plus c. This is for the parallel flow. Now we don't know what N and C is. Once we have the terms N and C, then we can find the effectiveness. So N stands for the number of technical transfer units, which is NTU, and C is the ratio of the heat capacities, that is C min over C max. Now what exactly is C minimum and C maximum? C minimum and C maximum are the heat capacities of the hot and cold fluids depending upon which is greater. For example, if we have a pipe wherein we have hot fluid flowing in and a cold fluid flowing out, there would be a specific mass flow rate for the hot fluid, and there would also be a specific heat for the hot fluid. Let's say we get some certain value, let's say we get it as 1000. Now we also have a mass flow rate for the colder fluid and we also have a specific heat for the cooler fluid. Let's say we would be getting this as 1500. Now in this case, this becomes C minimum and this becomes C maximum. The ratio of these two gives us C. Now once we have C, we need to find NTU. NTU is given by NTU or N means the same. It's UA over C minimum. U stands for the overall heat transfer coefficient and A is for the area, and C minimum is something what you extract from here. Once you have these terms, we can find the effectiveness easily. Now let us have a look at the question. You can have a look at the question here. So here, if we have to, once you read the question, we can just categorize hot fluid and cold fluid. Now one thing what I'd like to say is that whenever you have the mass flow rate, always convert into joules per kgs per second. Okay, so here we have the mass flow rate as 250 kg per hour. Now in order to convert it into kgs per second, we need to divide it by 3600. So for the hot fluid, the mass flow rate is given as 250 by 3600 kgs per second. Also, the specific heat of the hot fluid is given as 3350 joules per kg Kelvin. Similarly, I have the mass flow rate of my polar fluid as 1000 over 3600 kgs per second, and I have my specific heat as 4186 joules per kg Kelvin. Now, as I told you, we need to find out the respective C minimum and C maximum. So C for the hot fluid would be the product of MH and CH, and C for the cold fluid would be the product of MC and CC. This would correspond to give 250 over 3600 times 3350, which is 232.63 watt per Kelvin. Similarly, in here we would be getting it as 1000 by 3600 times 4186. We would be getting this as 1162.77 watt per Kelvin. So what we can infer is that this would comprehend to C minimum and this would comprehend to C maximum. Now as I told you, the next step would be finding out what C is. So we can write C is nothing but C minimum over C maximum. That would be giving us 232.63 over 1162.77. This would be giving we would be getting this as 0.2. As I told you, the next step would be calculating NTU, or the number of transfer units, which is actually given by NTU, or N is UA by C minimum. Here U in the question is given as 1160. The area is given as 0.25 meters square, and C minimum is 232.63. Now plugging in all these values, we would be getting it as 1.25. Now, since he's mentioned it's a parallel flow arrangement, if you refer the data book, the effectiveness for the parallel flow arrangement is given by effectiveness is equal to 1 minus e power negative n times 1 plus c over 1 plus c. Now we have the values of n and c. When we plug it, we would be getting it as 1 minus e power minus 1.25, 1 plus 0.2 over 1 plus 0.2. We are getting this value as 0.646. Now this is the effectiveness. We've solved the first part of the sum. Now he's also asking us the outlet temperature of the cool liquid and water. Now in order to find the outlet temperature of the cool liquid and water, we can use the above formula. The standard formulas, as we all know. So we know that the maximum temperature difference would be Q max, which is C minimum into THI minus TCI. The reason is that if you see the graph, the hot fluid cools this manner. The temperature difference of the hot fluid decreases and the temperature of the cold fluid increases. So the maximum temperature difference would be the difference between the hot fluid entry temperature and the cold fluid entry temperature. That's why we take the difference as THI minus TCI, and to balance it, we take C minimum. Right? This formula you can also find it in the data book. So when we plug in these values, we have 232.65. The inlet temperature of the hot fluid is given in the question as 120 degrees, and the inlet temperature of the cold fluid is given as 10 degrees. When I plug in these values, I'm getting my Q max as 25.59 kilowatts. We also have another formula for effectiveness, which reads effectiveness is Q divided by Q maximum. So we can write Q is equal to effectiveness times Q maximum, right? So we have a Q as the effectiveness, we got it as 0.646 times Q maximum is 25.59. So I'm getting this to be as 16.53 kilowatt. Now since we are trying to find the temperature of the hot fluid, the exit temperatures, so we have the respective formulas as Q is equal to CH times THI minus THO, where CH is nothing but, as I wrote, MH times CH of hot fluid times the difference between the inlet and outlet temperatures of hot fluid. So I have my Q, which is 16.53, is equal to the CH what I got here was 232.63 times my inlet temperature, which is 120 minus THO. From here I would be getting my exit temperature of the hot fluid as, don't mind, I'm just writing it here, THO would be 48.94 degrees Celsius. Similarly, we also have Q is equal to the same Cc times TCO minus TCI, because since the exit temperature of the colder fluid is high, we take it as TCO minus TCI. So we got Cc for the colder fluid as 1162.77. It would be 1162.7 times TCO minus TCI was 10 in the question. So plugging in these values, okay, so Q was also 16.53 kilowatts, right? So plugging in 16.53 kilowatts, that is, you need to multiply 10 power 3, you would be getting your TCO to be, just put in the calculator and see, it's coming around 24.22 degrees, 24.22 degrees Celsius. So we have the rest, even in here it's actually kilowatts, so I didn't put 10 power 3 in here, so just plug it as 10 power 3, and now we have the temperatures of our hot and cold fluid exit temperatures. So that's it as to how you need to solve the NTU method. Thank you.